So yeah, so I was speaking about the quantum internet testbed, what exists. So I'm not showing you here many more. Actually, there are tens of you know uh, this testbed, and I see immediately there is a question. So how could we use the state of plasma in quantum networking and internet? There is any connection of plasma state in quantum networking or the internet? So I'm not much familiar with the plasma, but photonic these photons what I was describing because of my experience, there are many different the particles you can use, okay, or I'm particles when we so for example the qubit can be in different states. Superconducting qubits are there, photonic qubits are there, and all sorts of the matter that you can discover which can hold the single particle that can form that can make the qubit and allow this to generate this superposed and entangled state. You can use it. Yeah. Okay, so where, I mean, apart from this, US, China, Europe has also its own quantum networks. And what in India, so basically what you see, Space Application Center, SAC in Ahmedabad, so they have demonstrated this quantum key distribution protocol, so-called BBM92 protocol, between two buildings situated over 300 meters apart, and also through the National Quantum Mission projects. The ISRO, so they will demonstrate the QKD or quantum communication, over through the satellite. So that's the aim. And here we have one funded, project between Delhi and Roorkee. So the idea is to develop the 6-node quantum, network, and which will go through the the Delhi to IIT Roorkee, and there will be intermediate nodes in between, and demonstrate various protocols. So quantum key distribution protocol, but also is what is not shown here is other protocols. So it's only mainly the QKD network, but we can also do the other switching, routing, etc. Of course, this is the linear network, so switching does not make much sense. But here, for example, for this node, at least you can see here, so it switching decision can be demonstrated whether when the data comes, whether it should go this way or that way, right? And in these networks, so a class is inspired by the classical, basically, right? So in classical, if you see, there are two types of switching, you can say, the circuit switching and the packet switching. I wanted to keep the slide, but it's not here. So in circuit switching, basically, if you want to transfer data, so you first reserve the channel, let's say from node number 6 to node number 3, right? And it's like a pipe, and then you can build a circuit, and then you transmit the data, right? So it's reserved. On the other hand, in packet switching, for example, what will happen, let's say you have data packets, and then you transmit it, right? At the intermediate node, it will read the and header it will check the IP address of the destination and some other information, and it will decide whether it should go this way or this way, right, based on the destination address, right? So in these two types of switch networks, so I mean, there is another, like, the question, how do we make these packets in the quantum domain, and like the classical, how the classical internet works today is the basically packet switch over the packet switch network, right? So these things still are the question, and in around 2028 this network will come up, and hopefully we will be able to demonstrate the QKD over hundreds of kilometers. Yeah, so there are many different, things that we need to work on, right? We have to use the quantum properties, build up the devices, and develop algorithms and protocols, and that will facilitate the quantum internet, right? So in devices, we have to develop the quantum processor, memory, the entanglement source, etc., right? Quantum protocols, algorithms, simulation models we need to develop. We need to demonstrate the entanglement distribution. We need to demonstrate so-called teleportation. Shortly, I described what I will describe you a little bit more in shortly. And quantum error correction. So, yeah, this is the main thing, actually. apart from. So if this is done, then I think scalability and these problems what we have today will be solved. So these are all are the open questions that one can work, and you can have your own company actually. So what are different challenges? So basically we also need to synchronize these different devices, right? And as the quantum state, let's say state psi, this propagates over fiber, so this state will not, it will lose its property, right? And also in the quantum memory, this state, if you store this quantum state, it will lose. Currently current standard is just few microseconds to milliseconds. You can keep one how it is generated, and after, let's say, micro milliseconds, then the same state will remain, right? So these are the very challenging questions one needs to answer. And yeah, as I said, the quantum processor, quantum memory, and with the optical interface, because today the long distance communication mainly happens over the the fiber. So this needs to be developed. And high speed, low loss. I will come to the repeater. What is the repeater? And again, the source detectors, etc. Yeah, needs to be developed, and actually many more what you can imagine. Okay, so yeah, these things are very important. Now coming back to, I think, one of the questions. So there is open system interconnect layers for the classical internet, but today's, if you look at this is 7 layers, but today's internet works on the 5 layer. So if you want to do any complex tasks, how is it done? You divide the tasks into subtasks, right? So similarly, these layers, they do the same thing, right? If you want to run any application, whether it's quantum or the classical, right? QKD, quantum key distribution, is one of the application. Quantum sensing would be another application. Distributed quantum computing would be another application. There are tons of applications, right? And application will run, and then you want the applications data to be processed, and if required, you need to be communicated, right? So how do we do that? Over the internet, right? So the classical internet has divided into the 5 layers, from application layer, transport layer, network layer, physical layer, link layer, and physical layer, right? Each layer has its own functionality, right? So application layer will run the applications, right? And transport layer will facilitate the end-to-end communication, will ensure that data is reliably transferred, right? Network layer will enable how the data will be transferred, let's say, from this node to this node to this node, and it goes to here. So from node 1, 2, 3, 4, how from node 1, for example, a data packet will be transferred to 3, because at intermediate node, this network node needs to decide whether the incoming data should go this way on this port or this port, right? So these are the things the network layer can do. Link layer will ensure the data, and based on the interface, what kind of frame, we call it frame. I'm not sure all of you are familiar, but I can easily kind of tell you. So combination of actually bits at the link layer. So it's just the different name of the packet, right? As simple as that. So how these data packets of frame will be transferred between the neighboring nodes, right? At what speed? Based on the here, what you see, the network interface card will be in. For example, you must have seen the 10G Ethernet port, right? So the network yeah. So that through which we connect. So NIC basically needs to be does this work. Let's say 10G or 100G, how the frame structure, how the data, these bits should be represented based on different protocols. Bits representation is different, right? Physical layer will take worry about the physical devices and how do you put this data on the wire. That's the physical layer. So quantum internet protocol stack is similar to that. Okay, so because people are trying to not reinvent the wheel but reuse it, right? So here in quantum domain, it will be done in the similar way. Okay, so yeah, so I will go one by one. So quantum physical and link layers we will see first. So in quantum physical layer, the aim is to develop the quantum devices that can generate or receive the qubits, quantum banded digits, right? Develop the have the quantum memory to store qubits, right? it has quantum fibers or free space links as a propagation medium. These are the role of the physical layer, right? How to put these quantum states on the wire or wireless medium, right? So that will be the role of the physical layer. Quantum link layer, basically it will ensure the entanglement states are basically generated from the point to point neighboring links and transferred. And how do you transduce, basically, right? Transduce, you have digital bits, and then you make it to the map it to the quantum bits. For example, 0, let's say I map it the photonic degree of freedom polarization. So I map it to the horizontal polarization. 1, I map it to the vertical polarization, but it can also be mapped into the superposed states. H plus V by 2, square root of 2, I'm dividing it because of the normalization, but also entangled states it can be mapped. Right. So how do we transduce the bits to the qubits? How do you couple the qubits to the quantum links, right? So that's another thing. And what kind of error correction codes do we need to use it? That will be the job of, this is the if you look at the lectures available on internet from the Psi Quantum, which is a famous startup or the company which has received the billions of dollars in the US to build the quantum computer. So yeah, so that kind of they are trying the scalability and the error correction are the key, the thing that needs to be solved before the quantum computer will come. Yeah. So how do we generate entanglement? Right? That's the question. Right. So if you have a single source, right? Forget about the network. Network has nodes, right? And then you interconnect them. If you have just single source, personal computer, right? For example, if it has the single source, what you can do, you can take the laser light, let's say at 980 nanometer, and you can pass it through the nonlinear clusters such as BBO, or there are other crystal, and which basically the idea is that lower this wavelength 980 nanometers. So basically when it passes to the nonlinear crystal, so the photons will excite the electrons in the BBO, let's say crystal, and that will release the the electrons again come back to the intermediate state and to the ground state. In doing this process, photons will be generated, right? Okay, so basically lower this wavelength, we will be able to generate a pair of photons, right? And they can be also entangled, meaning that now if the phase matching condition will be satisfied, and of course energy has to be conserved, then for example, let's say it here at one time this signal and another particle in the pair is called idler. If it is horizontally polarized, right, at that time this photon will be vertically polarized. At other time, if this signal photon, okay, wait, this signal photon is vertically polarized, I'm writing here subscript S so that you know, right, that time it will be horizontal, okay, just a minute, horizontally it's idler polarized, right? Okay, so but we don't know whether vertically or horizontally, from which left or right. You can couple it within the same fiber or different fiber actually. So what you see here, this kind of entangled state can be generated. Only thing is you don't know whether it's horizontal or vertical until you measure it, right? So horizontal, this signal, if it is horizontal, that is the idler signal is horizontal, then idler will be vertical. Vertical. This is one of the state. Another state can be horizontal, H as signal idler, plus I'm not writing the Ket notation, but it's okay. Vertical, signal and idler. This is another Bell state, plus minus also four. There are four Bell state one can generate, and this is between two particles. You can have the multi-partite entanglement also between three particles. So there are multiple different states one can generate. But the question is, in a network, how do you entangle the two remote particles or qubits, whether it's in memory or for the communication, right? So that's the key question that we need to answer. And no cloning theorem, as I described, actually hinders this thing. But how can we do that? I mean, so around, I think I have one of the slides in teleportation. So it's feasible. and we need to do something, right? So for example, before going to that, so there are two types of qubits we can use for this, remote entanglement generation. One can be used for the communicating, and another is for storing, right? So one can be the communication qubits, another memory qubits. We just define it, okay? So there are protocols, right? How to generate this entanglement between the remote qubits, right? So here what you see is that the brown circle is the communication qubit. Let's say these are just illustrative example, and yellow circle is the photons, which will be used for the communication or to the transfer, and the blue one is the memory qubits, okay? And yeah, so basically, and then we transmit the photons from these two end. Okay, why we do that, that's a different thing, but why? Okay, or let me tell you now itself. So basically we want to this the so-called Bell state measurement. Okay, aim, what is the aim? Aim is to entangle these two memory qubits. Okay, that's the aim, right? So the distributed quantum, and so the quantum state can be transferred and so on. And what is the Bell state measurement? Basically, you transfer here you have the source. You can generate an integral, particle. Here it's at remote. You can generate another quantum entangled state, right? But these two are not entangled, right? So how to ensure that these two are, let's say, out of 4 Bell states, which you will see soon. One of the states I have shown you. If we have to ensure that they are the same state, right, and entangled, right? So basically you propagate over the channel, and in the middle, as the protocol suggests, meet in the middle, right? So you transmit over the fiber, and use the beam splitter, right, to split whether it can go this way or this way, and use the polarization beam splitter. If you use this photonic polarization degree of freedom for entanglement, then you can use this polarization beam splitter and use the photodetector to detect it, single photon detector to detect it, right? All we need to, and based on its state, that there will be different clicks, and then you will measure the coincidence count, and if if the correlation is very high, or it's more than 50%, then we can ensure that what is let's say it is H signal V idler plus V signal H idler, right? Divided by, I'm ignoring the divided by √2, but yeah. So if it is both has the same state, right? So we will, by making this coincidence count, we will be ensuring that whether these two states are the same, right, and they are entangled, and they have this kind of state, or one of the entangled state, right, having this click. So yeah, so how does this meet in the middle scheme work? Basically, there are procedures which I can describe you simply. So first, each node prepares an entangled state between its own communication bit and the photon. So these two you can do it, right? And because it's at the same node, right? And then two nodes emit the photon simultaneously. Here, as you see, this one and this one, they transmit and meet in the middle, exactly in the middle. Why? This is this you will get to know soon, and perform this so-called Bell state measurement, okay, in the midpoint. Okay, then after this Bell, the Bell state measurement can be used with these devices, single photon detectors and linear optics devices, and if it has the certain more than the certain, the coincidence counts and success probability is more than 50%, then you can have this, you can call it Bell state measurement is successful, and this indicates that the communication qubits at the two nodes have already formed an entangled state, right? And then you can simply transfer the communication qubit to the memory state for the storage. You can put it here in the storage, you can put it, and then we will call it these two are entangled. Okay, these remote qubits are entangled. This is meet in the middle. Why it's in the middle? So because you see that the distance, right? If, otherwise one will arrive at after some the, how to say, so the photon is this polarization state also changes, right? So we need to synchronize that, and when it's in the exactly in the middle, so this state remains we assume that the ideal case. So both what we transfer from the left and right have the same, have the change is the similar change. Okay. Another scheme is the sender receiver scheme. It's also the same, but here Bell state measurement is performed at the receiver instead of in the middle. So it has, let's say, benefit over the meet in the middle. So sender photon again, you send the photon right from here, sender photon, which is entangled with its communication qubit. So it's sent to the receiver, and receiver prepares the entanglement state. So basically it has the entanglement source, and it's entangled between the communication and photonic qubit. It has its own, instead of transmitting in the middle. So once this left one it reaches here, it performs the Bell state measurement, right? And if the Bell state measurement is successful, then basically you need to also inform, actually, right? This step in the previous case, I think I missed, but you over the classical channel, or you simply inform the sender that the Bell state measurement is successful, right? And you inform the sender, right? And then you can perform any computing task. Okay, so basically the receiver is immediately aware that whether it's success or failure, right? So that's the benefit in this case over the previous case. Okay, so another is the midpoint source scheme. So here the entangled source is in the middle, right? Not at the one of the nodes. So, and the Bell state measurement is performed at the both nodes. And then after, if one and here again, after the Bell state measurement is successful, these two nodes have to inform each other that Bell state measurement is successful. Then you can say that these qubits are entangled, and you can store in the middle. These are the theoretical, by the way, theoretical propositions. And quantum repeater follows basically one of these schemes to regenerate the qubit, bypassing the no cloning theorem, actually, right? So without copying, you can basically transfer the information. So yeah, so this is the these are the things. Yeah. So how, by using these different protocols, how can we transfer the qubit state from one node to another? What you saw just now, to entangle, right? Two remote qubits. But how do we transmit the quantum state, right? So this can be done with the entanglement, so-called entanglement swapping, and the quantum teleportation. Okay, so what are these things? Basically, it's same thing we have described. So basically, what we want is that the quantum state at A should be transmitted at this, right? So in order to do that, first thing we need to do is the entanglement swapping, basically here. So let's say you have entanglement, entangled qubits from between node A and B, it's entangled, and between C and D, we want to swap this to here, basically. So this and this, A and B are entangled, and C and D. Basically, we want to entangle A and D. Right. This is the first step. How we can do? We can do the Bell state. We can perform the Bell state measurement, and we can have this entangled state in one of these 4 Bell states. And by performing this Bell state measurement, we will be ensuring the Bell state measurement. We will be ensuring that they are entangled, which we have already described, and we will call this entanglement is swapped, right, from node A to D. Okay, so yeah, so how do we transfer? Still we have not done that. So we have so-called the quantum teleportation in 1993. This theoretical paper published in Physical Review Letter. So again, this is the same Bennett, and that proposed the first QKD algorithm. So they came up with this idea. Okay, how can we do that? And it's all theoretical, and the experimental demonstration happened actually recently. So yeah, how do we do that? First, we establish this qubit entanglement between the remote nodes, right? And then we perform the Bell state, and then here is the quantum state we want to transmit. We perform the Bell state measurement between these two. And if the Bell state measurement is successful with the classical channel, we will inform, and basically it will generate the classical results, 2 bits results, whether it is 0, 1, 0, 0, or 1, 1. So based on the quantum state, it's all, and then classical results will, again, we have to do the classical operations, so-called phase flip, bit flip operations. And after these mathematical operations, then we will see that what you will generate here is the same quantum state, ideal states, this psi. So it will bypass basically node cooling theorem, and it will copy the state, QT state, from here, from node A to node B. So this is how one can transmit. Of course, when we do the experiment, in reality, it's much more difficult. But people have demonstrated in the lab, and hopefully, because of the noise and many other factors, yeah, it's challenging. But yeah, this is work in progress. Okay, so quantum repeaters, basically, what a repeater does. Repeater uses the TR mechanism: regeneration, retiming, and re-amplification, right? What we need to reach the same, let's say, energy state as it's transmitted after when a bit receives at a receiver, right? We need to regenerate. We need to also retime it, make it, because it's a stream of data, right? So we need to also retime it at the clock, so it's within its bit period. We need to ensure that retime, and of course we need to re-amplify it at the same stage, right? So what is the quantum repeater? It's analogous to the classical repeater, but of course it doesn't exist, right? There is no, one can use this meet and middle and or any other things to do that, but still it has not, people are trying to build up, but yeah, it's a difficult, and difficulty is caused by many, the photon loss and operational error due to the measurement, and you need to use some gates, quantum gates, for doing that. And until this error correction happens, quantum error correction is of course, in theory, there are many such propositions, but you need to, do so it experimentally, and the scalability, you can do it over, thousands of qubits, right? So until that happens, this is, yeah, work in progress still. So there are different kinds of, repeaters that has been proposed: first generation, second generation, third generation, based on the error correction capability, and etc. So I will not go into that detail, but you can read, just type and read. And if you ask me, I can also provide some links. Okay, so now you saw the basically the physical layer, link layer. In network layer, we will need actually the repeaters, and in the transport layer, if you look at the classical networking stack, then we have the two functionality of the transport layer, apart from ensuring the end-to-end delivery. So basically, you need to ensure the congestion control. What is it? I will explain to you shortly. And retransmission, right? So what is a congestion? So congestion is as simple. So you have, let's say, the data, right? This is node, this is another node, this is another node, right? So, and if I make maybe a little bit mesh network, right? This is transmitted here. This node may have its own data, right? It will transmit here, right? And this node, and so on. So based on the data rate and link speed, so these packets will arrive at this node, and this here basically switch or router, so it will transmit over, or the repeater. Repeater is just the in the repeater chain. So the router needs to have a repeater, right? So here this router needs to when the data is more than the link speed. For example, this link, right? It is 10G, and here it's 10G is coming, and this node will have its own data. So if the incoming rate is more than the outgoing link rate, then obviously you will have the congestion. And because this intermediate node switch or router, so will this one will not have sufficient amount of buffer, right? So packets data may be lost, right? So what we need to ensure is the congestion. So this sender, somehow this TCP protocol, when you will see the loss at the receive at the, let's say, the destination, then this needs to inform to the sender that, hey, your rate, you should reduce it, because I experience it will wait for the delivery of the data, because sequence numbers are maintained, and it will wait for the the data packets. So congestion control algorithm needs to be applied. Similarly, if data packets are lost, then it needs to retransmit. How do we do in quantum domain? This is still the work in progress. Over paper or theory, there have been some proposals similar to the TCP/IP protocol stack protocols, but yeah. So this is kind of complex. So how do we retransmit? I mean, this is the biggest problem, right? How will you regenerate the same data? Because in quantum memory, these qubits last for only for milliseconds, right? So yeah, this is still question, but this is promising. I mean, the quantum internet, because 1 decade ago people would not have believed that we will have a few qubits of quantum computer, but today we have, right? So over next decade we will have it, and because it the promise is so much, investment is so much, that hopefully we will have this realization. Now, uh, application layer, right? So there are many applications, right? One application is quantum key distribution. You can have quantum sensing application and other applications. But QKD, especially in India and China and the Europe, this is like the work that has attracted attracted the fund the government, as well as the private funding agencies. Why? Everyone is in the race to secure its data, right? China has around 2019-20s, China has demonstrated the QKD over satellite, okay, and also over the in terrestrial network, right? So people get worried. So if they, I mean, once you have the quantum computer, you can break the classical encryption. And today's classical encryption algorithm, it uses the prime number factorization methods to typically to get the key that will use, let's say, key, right? Key that will be used to encrypt the data, right? Simple case is, let's say you have single bit, let's say 1, you want to send it, and I have a key, right? So let's say 0, right? I do the XOR operation, okay? So what will be the result? It's a 1, right? Here is the key, here is the data. I call it key, this is the data. You have 1 as an outcome, and then you transmit over a channel, right? After it, I assume there is no loss of information. So after it receives 1, if the receiver has the same key, right, 0, then it will XOR with the 1, right? What is the outcome? Again, it's 1, basically your data. That's the simple case. We want to have this key generated in a secure way between two remote parties, right? That's the key. If it has the same location, there is no problem. Between two remote location, how will you generate the symmetric keys, right? And that's also, it's not one time generation. You have to generate and use it, and after use you need to discard it, such that the eavesdropper or the any third party should not try to get this key, right? So quantum key distribution, people have this misunderstanding also. It's encryption and these things, but quantum key distribution, the main role of this is to generate the secure keys between remote party. Nothing to do with encryption, in the sense that it only uses the key generation and distribution, not the encryption. You can use still the classical encryption method. For example, advanced encryption method, AES. Okay. Yeah. So as you see in this cartoon, so you when somebody calls you or sends you the friend request on Facebook, people got sometimes cheated, right? You need to also authenticate before you try to exchange the keys, right? Whether the person or the nodes are the right node I'm communicating with, right? So these are the the steps we need to be careful, right? So called the disturbance, right? So disturbance, is the eavesdropper, we call it in the quantum domain or the communication domain. So we need to secure these keys from the eavesdropper or disturbance, right? So idea is that if there is an eavesdropper present in the network, right? And here is the eavesdropper. This is, let's say, Alice, and this is typically name used for the sender and receiver, and Bob, and there is an if, presence of if. Can the Alice and Bob, can it determine the presence of if? That's also the key. That's also the the thing that we need to ensure, right? That's how it will. You can ensure that you have securely generated the keys at two remote parties, right? Quantum key distribution can do that. Okay, so yeah, and that will lead to be provable, provable information theoretic security key, secure key, basically generation at the remote parties. Yeah, so these are the things. Okay, so now before I describe that, you already know the quantum no cloning theorem, but it says that the unknown quantum state, unknown or arbitrary quantum state cannot be cloned, cannot be copied, right? Therefore, eavesdropper Eve cannot have the same information as Bob, okay? Because it cannot clone. It can get it at the let's say the eavesdropper in the middle. If it intercepts that, Bob will not be able to receive, right? The same. So through this, there is there's some steps. So that follow that step. So Bob or the receiver will get to know whether there is a presence of Eve, right? And you can use the single photon, right? Single photon as a signals, which is actually secure single photon. If eavesdropper tries to tap it, then it's gone, right? It cannot copy it and resend it, right? That's not possible. So that's how we can secure it. So the famous, researchers, professors Bennett and Bessard, in 1984, so they came up with theoretical idea of this so-called BB84 quantum key distribution protocol, and which is actually ironically, or I mean, the good thing is was published, in one of the Indian conference in 1984. And if you look at their kind of history and some conversation, so there this paper was not they were not able to publish their idea in the top conference papers actually. So couple of Indian professors, they invited them to this conference at IC Bangalore, and they did it. And after that, it was a kind of the big kind of revolution in the quantum industry. Still, it's a 1984, and today it's a 2010, right? So there have been, I mean, several years, and still we, I mean, see somehow the quantum products, these QKD products, but it has been a long time, right? So but it's a part of the the invention, right? So how does it work, the quantum this QKD protocol, right? So it uses basically non-orthogonal basis, right, to generate the signal and to receive the signals. Basis is if you so one is called the rectangular basis, and another is called rectilinear basis, and another is called diagonal basis, right? Here you have the capability to generate or receive the H and V polarized photons, and here basically diagonal plus 45 and plus 45 and minus 45, so diagonal and anti-diagonal polarized photons, right? So we can encode this in 0 and 1 in that way, right? So for generation, if it is 0, you can generate the photon polarized horizontally. If it is 1, you can make it you can encode it into the vertical polarization. If you use this basis for generation, you can do you can do this or measurement. You can represent 0 as a plus 45 linear polarized photon, and 1 for minus 45 linear polarized photons, right? And here aim is that between source and destination, or Alice and Bob, we have to generate this the secret key, right? So it uses two channels. One is called the quantum channel and another is called the classical channel, right? So quantum channel will propagate this entangled photons. I mean, it's not entangled in BB84, but there are other QKD protocols which uses the entangled the photons. But here it uses the simply this encoded the polarized photons, or discrete information in the discrete domain, like the polarization, to transmit over the classical channel. And the information what they have used, some information, they can be propagated over the classical channel also, right? So here there is a presence of if. In order to show that this protocol is secure, we assume that the Eve is present, right? Eve has access to both channels, classical and the quantum, complete access to the quantum channels. It can actually detect, get these polarized photons, and also it can listen to the classical. Okay, and these channels are ideal. There is basically only errors that will be introduced is due to the Eve, presence of the Eve. Okay, if it tries to tap it, measure it, then Bob will not receive that, and Bob can find it out. And there is no loss also. But basically this is the ideal channel. Okay, but in practice, when we try to implement it, you will see, I mean, these assumptions doesn't hold, and it's difficult to implement it. But there are new QKD protocols which can be used for the experimental some purposes. Okay, so let me do it in this example. So let's say Alice transmits this plus 45 degree, right? Plus 45 degree polarized photons, diagonally polarized, and Bob uses this basis to measure. What is meaning of this basis physically is very simple. When you do experiment, so basically you pass the, let's say, incoming photon through the polarization beam splitter, right? PBS, right? PBS, polarization beam splitter, and basically let's say H or V is passes, for example, H or V, you don't know here what is it, the state. And here you can use, basically this is a polarization controller, pad you might, I'm not sure, some of you might have seen. And here you have the polarization, and this single photon detector, right? So on these two are basically you try to basically how do you say, no. So this one should be here, polarization beam splitters. So this polarization controller should be here and not here. So here basically these three pedals, you can rotate it such that here the photon count is maximized, right? At this detector, it's maximized. So you can assume that if this is H, this is V. Okay. So basically on this polarization controller, you can make the HV basis actually. HV basis means rectilinear basis. Within by let's say here if you do the H, maximize the H, at that time if the source, right, typically laser source is the linearly polarized, you can use the polarizer also such that only H or V passes basically. Then you can do this easily. You can perform this experiment and maximize one of the arms automatically. If this is configured, then you know that H basis is configured. Similarly, you can also realize in experiments this diagonal and anti-diagonal by changing these paddles, right? You can also use the the crystals, right? The wave retarders, half wave plate, quarter wave plate, and these things. By rotating, basically fiber is there, basically twisting, you twist it and the polarization of the light changes. So by doing that you can make the, you can configure this basis and you will have different clicks, right? So horizontal and vertical, rectilinear and diagonal and anti-diagonal basis can be experimentally realized in this way. Now you see that if diagonal polarized photon arrives and you use this basis for reception, right? What will be the outcome? So because the basis you have prepared in this way, either this photodetector will click or this photodetector will click. There is only one single photon coming, right? So there is a 50% chance that it will go through this arm or this arm, right? 50-50. Right. So you may get either this or this, right? Let's say assume in this case you got this, right? Let's say next time you have this photon coming in vertically polarized and you use this basis. What you will have? You will have this vertically polarized photon receiving correctly, right? It's for example this one, and it will matches with this basis, you will receive the correct. If the basis is correct, right, matches with the how it is generated, then you will receive the correct you will receive the correct information, right? Now if you use the horizontal and use the diagonal basis, diagonal anti-diagonal basis, then you will receive either this or this with 50% chance, right? So let's say this, and this is how it works. Okay, so basically this is how is being explained here. So Alice transmits encoded this polarized information, and the Bob uses the random basis, right? It doesn't know which photons and polarization photons are coming, so it uses the random basis and generates some results, right? For example, this, it doesn't know which bits have been transmitted. So what they do, they exchange the basis after they do this measurement. They exchange the basis over the classical channel, right? Some of the bases, and whichever basis Alice and Bob has used the same, then they think that this what is has been generated on those positions, and if it is uses the right same basis, right, on those time slot, then those generated this key the bits is correct. But this is not the complete game. So what it needs to do is that some part of these bits generated has also needs to be shared with the Alice, for example Bob sends, to ensure that it's the same. Only some part remaining bits will form the key. Okay, this is last step is called the privacy amplification. And so this way Alice and Bob generates a secure key. Okay, and this is how it works. And if there is an if, it will basically intercept the photon, and there will be loss error will be much more than the ideal case. And you can, or the even in the experiments, you can have some threshold where you can say that, oh, if the loss is more, then you basically discard the whole process generation again and again, right? That can be done. So yeah, this is how it has been done. And basically, if you see the assumptions apart from these ideal channels, so in the source part, assumption is that it emits the single photons. Okay, no multi-photons. Channel is of course lossless, and detectors has the detection efficiency of 100%, which is not true idea in the reality. Bases are perfectly matched. Okay. And so this is how these are the assumptions, and if you have these assumptions in reality, then the QKD is secure. In theory, we will call it information secure, the QKD. But in reality, it is not. It's not like that. So typically, if you look at the single photon source, it will emit the multiple photons. Okay, instead of single photon. If you encode your bits into this photonic degree of freedom, then then multiple photons will be encoded in the with the same bit, and Eve can split in the at the intermediate on the channel. It can split these photons. These are our theory, right? It's still challenging, but one can do it, right? So it can split one of these photons, take it, another photon will go through the Bob, right? So Bob will not know the presence of the Eve. So yeah, but there have been many different advanced, this QKD protocols, which have been kind of developed. one of like this, another type of encryption is you can use the QKD to generate the this key, and then you can you can encrypt using the classical, or there is a term called quantum noise encryption protocol. I will not go into the details because I think we are running out of time. So you can do that. One of projects we have on this, basically you can use the intensity and of course phase, so different modulation scheme and the noise present in that to encode information in that. Last thing, okay, there are many different questions you need to answer, right? So how do we, transport the qubits? How do we, develop the control plane, management plane? How do we, build up these quantum repeaters, switches, and etc. So one good, very nice innovative thing that I worked was that you see how to develop this quantum packet. The problem is quantum packet is that in a typical data packet, you have the header and you have a payload. Header means that it will have the source address, destination address, length, and other checksum, etc. So error correction capabilities. This is header. This is payload. But the problem in quantum is that if you read the quantum data, it's gone. You cannot regenerate the same information at the intermediate node. So what we at UC Davis and the collaborator Professor Prem Kumar in Northwestern University, they proposed is that you can keep the header in the classic as a classical bit, and the quantum payload, and keep the quantum payload data in the quantum basically process, separate the quantum header and the payload, process the quantum header at intermediate nodes and transfer basically, and insert and so on. Yeah, with that I think I should stop and give you some time for questions. Yeah, thank you so much. Yeah, so do you have, let me see.
Any questions from the participants?
Okay, there were, I think, some questions. Plasma I saw whether high bandwidth application QKD is suitable. Whether, if so, why? High bandwidth applications QKD. What do you mean? I don't know. But I think typically you see the problem in quantum, as you see, is that the source what you have today, it can generate mega pair per second photons. So maximum rate that you can achieve is megabit per second. Typical number you can see the kilobit per second. So high bandwidth, I mean, even though fiber has high bandwidth, so you still, it's not it's not done unless you have this the source and the detector that can generate and receive respectively at the high rate. Yeah. And the high bandwidth applications, I see now why you asked. So to support, let's say 10 gigabit per second applications, right? You need to, if you want ideally the completely secure, communication, you need to have the key with the same rate, 10 GB per second, and that's not today is feasible. But even though you have the kilobit per second, you can use the linear shift registers, and of course there are security challenges, but yeah, that's how it works. What about side channel attacks? Yeah, channel attacks, yeah, it's feasible in the QKD. Not only that, actually, there are many different attacks that can be performed on the QKD. One typical attack is called man in the middle attack. Side channel is, of course, you can launch on the neighboring channel, and so Alice. Let's say Alice, or let me make it full, or let me make a new slide. Yeah, so yeah, Alice is there. Yeah, Bob is there. And let's say Eve is present in the middle, right? So if Alice sends, Eve receives. Eve will not send, cannot send the same information, but it can send the new information. It has the source. It can have the source. It has infinite amount of resources, right? Devices, money, and all. So it can basically it will form the secure key between this and this and this and this, right? So basically it will know, right, all the data actually. So this is also possible, but there is authentication mechanism that one Alice can always authenticate, over the classical channel, whether this is the right, person that to start the communication with. So yeah, these are the things one can do. Anything else? If there are no other.
Okay, so let's give a big thanks to Professor Sandeep Singh for taking his valuable time. And I hope the participants have got the overview of quantum networks and the challenges which are there. And probably they could connect with the concepts which they have already been learning for last 10 to 12 days. So effectively, probably now you are familiar with the challenges and some concept related to quantum networks. So thank you once again for accepting our invite as a speaker, and we are glad that you could take your valuable time for this particular session. Thank you.
Yeah, thank you, Rajendraji, and thank you all participants. Yeah, thanks a lot. Bye bye.
Bye.